Okay, so we finished derive the first equation. Let's try to derive the shear stress. Okay, so now we can see we had a normal kind of stress, the beam under different loads. And what we're trying to do is try to take a little piece out to do the analysis like I just plot. So if we were trying to take a look at here, make it bigger, so that we can see, okay, we had a cross-sectional area, and then we know on both sides we're actually going to have different moment, right? We had moment M on the left-hand side. We can assume on the right-hand side it's a little bit bigger, or slightly bigger, so we plus the differential moment here. So now you can see under those two moments, we can draw the stress distribution, right? And you can see the df prime, d double prime, df prime here, they are not going to be equal. And why? Because the moment is not going to be the same, right? The moment, one side is moment, another side you have to add the slightly different kind of values here. So now let's take a look at here. If we were trying to cut here, and if we were trying to take the top part as our kind of FBD, so you are going to see the three-dimensional VU like this. So if we were trying, or the 2D kind of VU like this, you can see there is a mismatch, right? So if we try to summarize the total area of this side of the trapezoid and another side of the trapezoid here, you can see it's not going to be under equilibrium, right? So this is going to, we say this is F1, the total force here will be F2. You can see they're not going to be equal. Their area is going to be different. So that's why we got to have something to balance it. We say this is going to be F3. So that's actually the mismatch in the normal stress. So now let's try to derive this equation here. So we can see for the F1, the total force here, that's actually going to be the integral for this area for the sigma here. And we know the sigma, it is equals to the my over I here. So we can do the same thing for the F2 force calculation. However, the M is going to be slightly different, right? It will be moment plus the incremental things and like this. Okay, so now let's see what is F3. So the F3, if we were trying to use the 3D, you can see there is something distributed in this area here. And you can see the red arrow is actually parallel to the cutting plane, which is the yellow plane I just draw. So which means that's actually going to be the shear stress. And then it's times the area here. Okay, so you can see if we were trying to summarize the force in the x direction, so the mismatch, so F2 minus F1, that's actually going to be the F3. So now you can see F2, which is this equation minus the top equation here. So the only thing left for the F2 minus F1 here, that's actually going to be the differential moment times y over I here, and times the dA. And this is actually equals to the shear stress times the dA. Okay, so now let's take a look at here. We had shear stress F3, and then we need to find out the dA. So what is the area for this yellow area I just shade? You can see that's actually the dx, the width, and then times the cutting width here, which is the T. So which means if we combine all of them together, we should be able to have the tau, the shear stress, is actually equals to this one. And then let's try to move T and dx underneath here. And then we had a dA. So let's try to rewrite everything here. We had a dm over dx, and we had integral. So, and we had integral ay dA. And then we had moment of inertia underneath. We had a t here. So now let's take a look at here. What is dm over x here? That's actually the slope on the moment diagram equals to the shear force, right? And then we had integral for y over the whole area. So here we are going to give it a new name. It's called Q here. It's the first moment of inertia. So remember the I moment of inertia is equals to the y squared dA. So now we had a new term Q equals to only first. It's not the second here. Okay, so now which means we are trying to rewrite everything so the tau here is equals to the V Q over IT. So this is the transverse shear stress under the internal shear force for the beam here. So the Q is the first moment of the area, and the Q here, so let's move to the next page. I had a note here. So the Q here is the officially this equation, but most importantly, we like to use AY bar to do the calculation for the regular area. And then the units for the Q is going to be the length cube. Okay, so now the last derivation I want to go through is here, the shear formula. So you're probably going to say, hey, when we try to do the derivation, remember we had the cross-sectional area, we do the cut here. And we are trying to use the top part as our FBD. And then we find out the shear stress here. But how could we find out the transverse? Because normally our shear stress is actually going to be drawn like this. Because on this cutting plane here, if you had a shear force going this way, then that's actually going to be the shear stress distribution here, the tau. Okay, so do you remember when we try to plot the shear stress here, if we find out the stress on one end, and then we just do head by head, tail by tail, that derivation video I made before. So we are going to do kind of like the similar situation here. We find out, yes, we did only find out the tau on the cutting plane. However, because the shear equivalent here, that's actually equals to the same head by head here. So that's why we can try to plot our shear stress distribution like this. All right, so let's summarize what we had derived today. So for beam, we do had shear and bending moment here. So now, under these two internal force, we had normal stress, sometimes will be called flexural, stress it will equals to the my over I, and the transverse shear is equals to the VQ over IT. So these two equations are very important for any of the beam, because we are going to use those two equations as a guideline to do all the design work.